Okay, welcome to EGR 550 Mechatronic Systems. In the very first class, I gave you a broad overview of the concept that we are going to talk about. We looked at what do we mean by system, we looked at what do we mean by dynamic model, we looked at what do we mean by stability. We also looked at briefly how to look at the frequency response, what do we mean by Bode plot, and so on and so forth. Now, in next few lessons, at least next 3 or 4 lessons, we are going to explore these concepts in a lot more detail. And I'm going to follow the textbook the way it is presented. So first we will look at chapter 2, which is on the dynamic models and analogies. What I want to tell you is, if you look at the mechatronic systems, it's the mechanical system and electronic systems working together. Now, many a times you would observe that these systems, they have similarities. So if you have a mechanical component, you are going to have an electrical or thermal component that is equivalent of mechanical component. For an example, you have something called as inertia. So you are going to have similar inertia in case of thermal systems. You are going to have similar inertia in the case of fluid systems. You are going to have similar inertia in the case of electrical systems. In the case of fluid systems, you have flow. In the case of electrical systems, you have current. So what I want you to understand is the constitutive relationships, the fundamental relationships that describe the behavior of these systems, they are similar. Only the manifestation, that the representations could be different. That's why there are different techniques that can be used to describe the equations that describe the electrical system, the mechanical system, or for that matter, the thermal systems. They may be same. And that is the beauty of it. So if you look at the textbook talks about different techniques to model these types of systems. One is using a block diagram representation. One approach is looking at maybe differential equation. Second approach is maybe system identification, coming up with some experimental models. There are graphical techniques wherein you can use graphs, linear graphs or bond graphs to come up with these relationships. So we are going to talk about what different techniques are available to understand the behavior of these systems, and then how do we analyze and solve these systems, and then finally how do we see or observe the behavior of the practical system, and how do we correlate that with the mathematical model that we have designed. So again, if you have a mechanical, electrical, or any physical system, so what are we looking at? We are looking at, so what are we trying to study? So what are the procedures and techniques for analytical modeling? Then how do we perform the simulation and analysis? And ideally we want to, yes, ideally what we want to do is we want to develop some uniform techniques for analysis and simulations, so that whether we have electrical system, mechanical system, or thermal system, we use the same set of tools to understand and analyze those systems. So for an example, we want to have certain tools in our toolbox that will allow us to analyze whether the system is mechanical, thermal, fluid, or electrical. And the next thing is, what are the similarities between these different systems? What is the equivalence between these different systems? And then how do we do multi-mode or multi-models analysis, which means we have a thermal mechanical system, or if we have electromechanical system. So how do we study these types of systems? And please understand, when we are trying to model, we are looking at systems that are actual systems developed in practice. But from mechanical point of view, we can't analyze the actual practical systems. We need to make certain assumptions. For example, if you have a distributed system, say for example, the mass of this textbook is distributed. But if I want to analyze, what I can assume is the mass of the textbook is located at the centroid of the textbook. And that is the assumption that is called as the lumped mass assumption. So the entire distributed mass is focused or lumped at some certain point. Then we have to find out what type of sources, sinks, and interconnects they exist in these systems. Then there are two important concepts. So whenever look at mechanical, electrical, flow, or thermal system, there are some variables that are across the system, and there are some variables they flow through the system. Let me give you a very simple example. What do I mean by across variables and what do I mean by through variables? So if you have a fluid flow, flow is the variable that is throughout. You have point A, you have point B. So you have flow that is going from point A to point B. If you have current between 2 points, you have a conductor, you have current. So the current flows from point A to point B. Now, what makes that flow flow? That reason for that is potential difference. Potential difference is across variable, flow is through variable. Similarly, the voltage difference is the across variable and the current is the through variable. Temperature difference is basically the across variable and the heat or the heat rate is the through variable. So there are across variables and there are through variables. So we look at these different variables and their relationships. There are graphical tools of analysis. There is linear graph, there is bond graph that can be used for analysis of electromechanical systems. Also, there are block diagrams. Now, there are certain concepts like input, output, causality, and system order. So I need to mention this before we get into the details. Input is causing that system to respond, and output is the response of the system. So I just need to explain a few things here. So if you think about it, input is that is causing system to respond. Output is the response of the system. Now, the next important thing is, what is causality? So what is causality? Now, what this means is output is function of inputs and the system state. So in other words, there is certain relationship between the input where the system was and what is the next state of the system. So there is this cause and effect type of relationship that is basically causality. So one simple example is you have this complex system which is like a transit system, a rail system. This is a distributed parameter system. So if you want to analyze, we can't analyze this system with its hundreds of degrees of freedom, hundreds of springs, thousands of damper, different masses. So what we do is we actually approximate this system into some simple representation that is easier to analyze. So for an example, if you look at this car, I'm going to treat this as mass with say 3 degrees of freedom. I'm going to assume that this mass is attached to the rail with multiple springs, multiple dampers. And then I would analyze the motion of this car based on the input and the previous state of the system. Same thing happens with a hard disk drive. So this is the old computer hard disk. This is not an SSD, wherein you have the head. So that you have this head that actually moves on this disk, and then the data gets written on certain sectors of the disk and it gets retrieved. So the way to approximate the behavior of the system is with this some type of a simple model. So this simple model comprises of some mechanical elements, that is like spring, mass attached to another spring and attached to another mass. And once we write the mathematical expression that describes the behavior, we kind of predict what would be the future behavior of that cylinder head. So this is a very simple model that is representing the computer disk drive. So this is what a dynamical system is in broad sense. So what we have is we have some state variables, we have some system parameters, there are some external inputs, and the system would respond to these external inputs and provide some outputs. There will be a system boundary that separates the system from the surrounding. So for an example, you can have some outside temperature effects. So those are the environmental effects. You have external forces. Those are the inputs. So the system response would be dependent on the input from the environment, the current state of the system, and the current forcing on the system. So in the last class, I briefly talked about the nomenclature of a mechatronic system. So you have system, which is the connection or interconnected components of interest. Dynamical system is the system that is not static, the system that is moving, system that is changing states, which has some response to the external input. Then you have something called as plant or process, that is the system to be controlled. You have inputs that are excitation, outputs that are responses. The state variables are nothing but the state variables are the degrees of freedom that identify the system completely. For example, if you have a mass, okay, if this mass is moving, then to locate where the mass is, you need to know the position and you need to know the velocity. So position and velocity are the two states of this mass that are required to identify where the mass is and what is mass doing. Now, I just want to emphasize that when we deal in macroscopic world, like the world we live in, we have distinct degrees of freedom. So we can separate out positions from velocity. But when you look at the microscopic, essentially when you look at the quantum world, you cannot distinguish position and velocity separately. That's why when you look at the quantum effects, you have something called as the Heisenberg's uncertainty principle, which means you know where the particle is, or you know what is the momentum, or in other words, what is the velocity of the particle. So you can't determine these two both simultaneously. You can't determine the location and you can't determine the velocity of the particle at the same time. So that is what something happens in the quantum world. Control system is something like you have the mathematical model for the system to be controlled, and you have some type of algorithm and some type of actuator, some type of microcontroller, some type of computer that is implementing that algorithm and that is controlling the behavior of that system. This is a quick review. Like if you have different types of systems like human body, if you have an organization, if you have a power plant, if you have an automobile, or if you have a robot, what are the typical inputs, what are the typical outputs, and many a times this is very important, and we are going to do this when we actually perform the experiments. Many a times what we understand, we try to look at the relationship between the input and the output and try to model the system. So for an example, some systems can be modeled as a zeroth order system. So let me give you a very simple example. Imagine that I have this spring balance. Okay, I have this spring balance. As soon as I input certain amount of force, I get certain amount of deflection. which is delta, which is output. So what I have is I have input and I have output. So once I know the relationship between input and output, so here is what I'm going to do. So I'm going to plot the force as input here and displacement as output here. So I notice this, when the force is 0, output is 0. I add certain force, I got certain output. I add certain force, I got certain output. I add certain force, I got certain output. And it tells me something very interesting. What this tells me is the relationship between the output and the input is linear. Everyone agrees with me? There is no delay between the input and the output. As soon as you apply the input, immediately you get the output. This is the characteristic of zeroth order system. Now please understand. Now my output is x, and my input is force. And there is this constant, which is I'm going to call 1 over k. This is x is equal to 1 over k multiplied by force. This simple equation describes the behavior of this spring balance. Everyone understood this? What I'm going to do here is I'm going to rewrite this equation in a slightly different form. I'm going to ask you this: x is equal to 1 divided by k times f. I'm going to ask you, what is the highest order of derivative in this equation? What is the highest order of derivative in this equation? Is there any derivative in this equation? Is there any x dot? No. So the highest order of derivative in this equation is 0. So in this equation, the highest order of derivative is 0. That's why this is called as the zeroth order system. So what do we observe? We observe when the system is zeroth order, the relationship between the output and input is maybe linear in this particular case. When the system is zeroth order, the system behaves instantaneously. So you supply the input, you get the output.
Okay, Satyam theater bolan. Satyam theater bolan ta ye video.
Pardon me?
So they are like, huh?
Do you have any question? Okay, if you have any questions, just unmute yourself or just raise your hand, and then you are welcome to ask me your question. So in this particular case, this is the zeroth order system because the system behaves instantaneously or responds instantaneously to input. Now what I want to do is I want to add one level of complexity to this system. So imagine this is what I do. So you have system like this, and you have spring, and you have damper. Now you have spring and you have damper. Now what would happen? Do you agree with me? Since you have damper, I'm going to add force. I'm going to add force, and I'm going to measure the displacement of this system, x. You would realize that the system response will no longer be instantaneous, which means because there is damper, what's going to happen is the damper is going to respond sluggishly. Spring would respond immediately, the damper would respond sluggishly. So what that means is you are going to have not only instantaneous response, but you are going to have some type of a sluggish response. And this sluggish response is the characteristics of the first order system. So this system is first order system. And I just want to kind of take this and take it a little bit further. So what I'm going to say is this distance is x. So this is my datum. So this is my datum. This would be at position 0. The damper, velocity of damper at this point is going to be x dot. So the force is going to be equal to k times x plus, I'm going to call this c times x dot. So external force F is equal to k times x plus c times x dot. If you were to draw the free body diagram, you would observe you have a downward force F, you have an upward force Cx dot, and you also have an upward force K times X. So summation of forces in y direction is equal to 0, and you get this type of equation. Now my question to you is, what is the highest order of derivative in this system? The highest order of derivative in this system is 1. So this is the highest order of derivative is equal to 1. This system can also be represented as in a slightly different fashion. So you can actually simplify this, take K and C on one side and write this as a simple first order system. But let me add something else to it. So now what I'm going to do is consider you have spring and you have damper and now you have mass. And all of a sudden you have the inertia force mx double dot, you have the spring force which is kx, and you have the damper force cx dot is equal to external force, and now this becomes the second order system. And what happens in the case of second order system? In the case of second order system, you are going to observe that the output would be attenuated. So if you have the input like this, the output will be attenuated, and then the output would be out of phase. So this is the input and this is the output. So this is called as the second order system, spring, mass, damper system. So why do we need dynamical models? So here, this equation, here, this equation and here, this equation is called as the dynamical system model because it shows how the system is going to behave in future. This is a differential equation. So if you want to find out the solution of the differential equation, what we do is we integrate this equation 2 times, add 2 constants of integration, and boom, once we know what the input is, once we know what is the previous state of the system is, we can find out the future state of the system. And that's why we need a dynamical model. So dynamical model is a mathematical representation of a dynamical system. It is used for analysis, modification, and control of that system. The engineering system, like a mechatronic system, can consist of mechanical, electrical, electronic systems. So basically it could have different types of systems. Then what we want to do is we want to come up with an engineering representation that is useful to understand system behavior. We want to develop an integrated model that is easier to analyze, and we want to make sure that we understand the physics of the system. Now, most of these models, they are based on energy principles, because please try to understand, conservation of energy is a fundamental law that governs the universe that we live in. Energy can neither be created nor be destroyed. It only changes form. So what you would observe that whether it's an electrical system, whether it's a mechanical system, whether it's a thermal system, whether it's a fluid system, the formulations are based on energy balance. What is energy coming in? What is energy going out? And those energy balance equations, they help us derive these differential equations. And we'll talk about how to use the energy techniques for derivation in a little bit later. But please try to understand the fundamental principles of the universe are same. They are energy based. So you can use the energy principles to derive the mechanical models of variety of systems. Let it be a mechanical system, let it be an electrical system, let it be a fluid system, let it be a thermal system. You can use the energy principles to derive the relationships. And those form these analogies in mechanical, electrical, and fluid and thermal systems. Why these systems are analogous? Because they follow the same fundamental laws that are based on energy principles. What are the different types of models? There is a physical model. A physical model is typically used in experimentation. So let's make the model. Let's 3D print the components. Let's machine the components and let's have that component made. And then we can test it and then see how the system behaves. There could be analytical model, which means the model that is based on the math. So the differential equations. So you can have ordinary differential equations, you can have partial differential equations, you can have integral differential equations, you can have a hybrid or combination differential equations. You can have computer or numerical models because those come from lot of data and you come up with some data driven models. There are some experimental models, which means the models that describe the relationship between input and output that is purely based on experimental data. Any type of theory or no first principle analysis. And we'll try to look at through these different models. But amongst these four models, we prefer to use analytical models or we prefer to use computer models for a very simple reason. Analytical models, which are derived from either Newton's laws or energy principles, they are derived with some basic assumptions about the physical properties of that system and the constitutive relationships like energy principles. Numerical models are derived from the data that is available or some type of approximation. So for example, if you have a partial differential equation in theory has infinite degrees of freedom. So what you do is you kind of approximate that infinite degree of freedom differential equation into a finite degree of differential equation. I want to give you a very simple example. Now, imagine, and this would be a good example. And my online students, I'm going to turn on the camera so that you can observe this quick demonstration. So I have this scale in my hand, okay? And I want you to observe that as I bend this, it starts vibrating. Okay, as I bend this, it starts vibrating. But this vibration, this motion is in the vertical plane. So this is the motion, okay? The magnitude of this vertical motion, okay, or the amplitude of this vertical motion depends upon two things. depends upon where the point is on this scale. In other words, the spatial dimension where this point is, spatial dimension, and what time is it. So in other words, this scale, if I want to describe the motion of any point on this scale, I need to supply two things. I need to supply the time value and I need to supply its location. I'll give you a simple example. Imagine this scale is held fixed in one hand and now it's going up and down. Here, since this is rigidly connected, no matter what time t is, this is not going to move. And that's not going to move because its x, horizontal distance here, is 0 and this is fixed. On the other hand, when this x is equal to L, as you can see, this motion is significant. On the other hand, when I'm at the mid span, half of the length, this motion is not significant. So what this means, the differential equation that is describing the motion of the scale has two independent variables. What are these two independent variables? One is time and the other one is the distance. So now I have the mathematical model. So if I want to come up with a mathematical model that shows the behavior, this vibration of the scale, it will have two independent variables, not one, but two. Thus, the differential equation that will describe the behavior of this system will be a partial differential equation. Why? Because it's going to be dependent on two independent variables. Now, on the other hand, I want you to notice this is the box. And if I want to observe the vibration of this box, it's going up and down. I don't need to specify where that point is because all the points are going up and down in unison. They are not dependent on the x distances. So the independent variable in the case of oscillations of this box is only time. What it means, the differential equation that is going to describe the behavior of this box will be ordinary differential equation because one independent variable. So if you have one independent variable, it's ordinary differential equation. If you have more than one independent variable, 2, 3, 4, 5, 6, 7 thousands, that would be a partial differential equation. Everyone understood this? Online students, any questions? Okay. So next thing which I want to talk about is complexity. So as you can see that if we were to look at the lumped mass model, we are making certain assumptions that reduces the complexity of the model. But if you want to be as realistic as we can, we have to relax these assumptions. So for example, if you have an automotive a model, depending upon what parameters that you want to measure, you can treat this as a lumped mass model, or you can actually add mathematical models for various components and subcomponents, and then you are going to have a very complicated model. And depending upon what your needs are, depending upon what you are trying to find, depending upon what your goals are, depending upon amount of computational power that you have available, you can use a very simple model or you can use a very, very complex model. But as a thumb rule, your model should be as simple as possible to give you the best possible result. So that is something that you should keep in mind. So your model should be as simple as possible so that you can solve it in a reasonable amount of time. So what are the advantages of analytical model? So analytical models are virtual models. In physical models, you have to actually build the model, test the model, and it's time consuming. It's very expensive. On the other hand, analytical models can give you reasonably good data if your assumptions are correct, if your constitutive relationships are correct, and if the parameters that you measure or assume they are within the experimental limitations. So, and you can modify those very quickly. You can design the controller, you can use some type of optimization routine to optimize those models, and so on. So typically the analytical models or numerical models are preferred than the actual model. Imagine if you want to test or design an airplane. It's impossible to build thousands of those planes and test those. On the other hand, you will come up with a mathematical model, validate it, and then finally come up with one or two test cases. And for those one or two test cases, it's practical to build those airplanes and test them and validate. But realistically, it's not possible to validate for hundreds of variations. Now, there are different types of models. You can have a nonlinear differential equation. So what I want to tell you is this is something super important. So let's understand what do we mean by a differential equation. Differential equation, which means the equation that has derivative. Now there are two types of differential equations. One is ordinary differential equation, and partial differential equation. So what is the ordinary differential equation? There is only one independent variable. So one independent variable. And more than one independent variable. So how would we write this independent and dependent variable? So I'm going to say y is function of t. And in the case of partial, y would be function of x and it would be function of t, where y is the dependent variable and t and x are independent variable. So if I want to write down the differential equation, it's going to be y dot, which is dy by dt, is equal to, say, y. So y dot is equal to y is a ordinary differential equation. What happens in the case of partial differential equation? It will be something like partial y by partial x plus partial y by partial t is equal to y. So this is one partial differential equation. Now understand, this is still a linear differential equation. This is also a linear differential equation. Now there is a possibility that you can have y dot is equal to y square, and you can have partial y by partial x plus partial y by partial t is equal to 1 by y square. And this is a non-linear differential equation. This is non-linear. This is non-linear. Now, sometimes you can have, there are some equations which are called as autonomous differential equation and some equations which are called as non-autonomous differential equations. What do I mean by autonomous differential equations? If you see in this equation, the time does not exist. There is no explicit mention of time. So these are autonomous. You can have a differential equation, something like, say, m t y square plus ty. This is non-autonomous. Because now the time explicitly is present in this differential equation. So autonomous means that it's autonomous vehicle, which means it can drive on its own. So here, when there is no time involved explicitly, the differential equation is on its own. Once the time is explicitly mentioned, the differential equation is no longer autonomous. That's why it's called as non-autonomous. So these are various types of differential equations. You have a nonlinear differential equation, you have a linear differential equation, you have a partial differential equation, you have an ordinary differential equation, you can have a time varying non-stationary differential equation, you can have time invariant differential equation, you can have stochastic differential equation, you can have a deterministic differential equation, you can have continuous time, and you can have discrete time differential equations. So these are the different types of differential equations that you encounter when you study mechatronic systems. Now I'm going to go one by one, and I'm going to ask if you know, if you are comfortable. Everyone comfortable? What do I mean by nonlinear differential equation? Does anyone need an example? Linear differential equation? Distributed continuous parameter is nothing but the partial differential equation. Everyone okay with partial differential equations? I'm not asking that if you can solve these differential equations. I'm asking, if I were to give you an equation, will you be able to identify whether it's a linear, non-linear, partial, ordinary, and so on? Lump parameter is nothing but ordinary differential equation. Time varying, which means where time is present in the equation. So for an example here, can you see this t is present here? This t is present here. So this is a time varying differential equation. Everyone understood this? Time invariant. What do I mean by time invariant? Time invariant means the equation like this. In this equation, m, which stands for mass, is not changing with time. Mass m is constant. What is an example? Imagine you have an aircraft flying. Aircraft has a fuel, and as the aircraft flies, the weight of the aircraft, in other words, mass of the aircraft changes. So the differential equation that describes the motion of the aircraft is time varying, because the mass is changing with time. However, if you just have this box which is going up and down, its mass is not going to change with respect to time. So it's time invariant. The system parameters or mass, stiffness, damping, they are not changing with time. But for example, rocket, the mass of the rocket changes significantly as seconds pass by, because it's burning so much amount of fuel. It's dropping all those rocket motors and the mass is changing. So the differential equation that describes the behavior of the rocket is time varying. And then you have something called as the deterministic differential equation. Deterministic differential equation means there is no randomness, that it's not statistical parameters involved. You have random differential equations or stochastic differential equation where there is some randomness, some random parameters that are involved. So in other words, you can't just provide a particular value of mass. You would say this mass could have certain mean, this mass would have certain standard deviation. And when you try to solve the stochastic differential equation, your answers would not be deterministic. You cannot say by certainty that if my mass is varying within this mean and this standard deviation, I would be at position X. What would happen is when you solve a random or stochastic differential equation, you would say, since my mass is varying within this standard deviation and this mean, my position would be within this particular range with certain standard deviation and certain mean. So, and if you study quantum mechanics, or if you get exposed to quantum mechanics, what they do is they study something called as the wave functions. What are the wave functions? Wave functions are nothing but it's a random variable. It's the probability where that electron would be in that electron crowd. So Heisenberg uncertainty principle states that you cannot determine the position and the velocity at the same time, because these parameters are stochastic. These are random. Essentially, those two are Fourier pairs of each other. But what it means is you can have a probabilistic understanding of where this electron could be in this all possible space, and that is nothing but the wave function that is studied a lot. That is the cornerstone of quantum mechanics. So if you study quantum mechanics, particle physics, you would study this wave function all the time. So next thing is, if we have a continuous parameter system and if I have a lumped parameter system, what are the advantages and disadvantages? So let's try to take an example wherein I have this spring. This spring, typically, so far what we have studied, when we try to model springs, we ignore the mass of the spring. We say that the spring is massless. Now what I want to say is, imagine, you can't have massless springs. All springs are going to have mass. Imagine I have this heavy duty truck spring. This has significant amount of mass. So how does the behavior of the spring change when I introduce the mass or the self weight of the spring? And most of the times, whenever you have these types of distributed systems, we tend to use some type of energy based approach. So here is what is the basic assumption. So again, I want you to look at this problem from physics point of view. Imagine that you have this spring. This spring has some mass. Small m of s is the mass of the spring. If this spring is pulled on the free end, fixed end is going to stay where it is and the free end is going to move. Now the assumption here is velocity of the free end. Velocity of the free end is proportional to where it is from the fixed end. And some of you may say, what is the justification for this logic? The justification for this logic is, let's go back the very first concept that we talked about. Imagine that I have this mass. Okay, if this mass is fixed, no matter how much I pull on the right hand side, nothing is going to move. Do you agree with me? Because this mass is not going to stretch, at least not noticeably. But now what I have is I have spring. I apply the load. So this spring is going to stretch. So my basic assumption is the velocity of the free end is proportional to the location from the fixed end. So what that means is the velocity at fixed end is going to be 0. Velocity of the free end is going to be maximum. Everyone understood this? That is the assumption I'm going with. So this is called as the local speed. So I'm going to call this local speed is dependent on the position divided by the total length multiplied by the velocity of the free end, and I'm going to call this delta x. Again, I'm going to assume that the mass is distributed, and I'm going to use the same proportion for distributed mass. So this total mass is spread across the length of the spring, and the mass of the segment of the spring is proportional to that distance x. So I'm going to say delta m is total mass divided by the length multiplied by delta x. And now what I'm going to do is I would use these to find the kinetic velocity, kinetic energy. Kinetic energy is given as 1/2 mass times velocity square. Now please understand, this is the distributed system. So what I need to do is I need to take these particles, this first particle, then I need to take the second particle, then I need to take this third particle, fourth particle, fifth particle. I have to write down the kinetic energies of each and every particle and integrate it over the length of the element. So what I do is I write this expression for the kinetic energy and integrate this whole equation over 0 to L. And what it tells me is the kinetic energy, and this is very important, kinetic energy of this spring with distributed mass is 1/2 mass of the spring divided by 3 v square, which means this lump mass, 1/3 of the lump mass is contributing to the kinetic energy of the system. So in other words, if I have, so what does this mean? It means if I have a spring, and this is the takeaway, if I have this spring and this spring has mass ms, if this spring has mass ms, and if I want to understand the behavior of the system, to understand the behavior of the system, I can approximate this as something like I have a spring which is massless. This is massless spring. And at the end, there is this mass, which is 1/3 of the total mass of the spring. So if I have this spring, if I have this heavy spring with mass, if I want to understand the behavior of the spring, I would convert this into a spring which is massless, and the mass that is attached to the end of the spring, but that is 1/3 of the total mass of the spring. And when I analyze this, the response of this guy would be same as the response of this heavy duty spring. Everyone understood this? Any questions here? So this is what it means. So if you have, here is a simple example where what you have is, you have a spring. This spring is heavy duty. This spring has mass K, mass ms, and the spring stiffness is K. And this heavy duty spring is attached to mass M. And if I want to analyze this, the right way to analyze, I need to take into account the mass of the spring, then 1/3 mass of the spring gets added to the mass M, and then what you do is you analyze this system as if you have this additional mass at the end, and that would be the differential equation of motion that will be used to derive the differential equation of motion. Everyone understood this? So now what are the steps in developing an analytical model or mathematical model? So you have to understand the physical system properties. You need to understand the system boundaries. You need to understand the energy interaction. You need to understand the independent dependent variable, and then you need to understand the overall dynamics of the system. So again, when you try to solve for the dynamics, you have some type of energy transfer taking place, and you have some type of compatibility taking place. What do I mean by compatibility? Compatibility means, imagine that you have two joints or two objects connected with each other. Compatibility means when one object moves towards right, the other object is moving towards right. So this is the compatibility. So basically you have at the boundary, you have some type of uniformity, some type of compatibility that allows you for a smooth energy interaction. Otherwise, if this object is going to move towards right, but this object is not going to bulge, then there won't be a compatibility and there will be failure. So compatibility means, say, expansion of one means the contraction of other or compression of other. So you need to have, so I give you another example. Say if you have a pipe joint, two pipes coming in, one pipe going out. So what do we mean by compatibility? Compatibility means all the flow that is coming in from these two pipes need to go out from the second pipe. So two pipes flow coming in, the third pipe is carrying the flow out. If the third pipe is not carrying that complete flow, then what would happen is that joint would bulge and eventually break. So compatibility means you need to make sure whatever is coming in, that is going out. Now, I briefly talked about the through variables and across variables. Please understand, energy principles are everywhere. Mechanical system, electrical system, electronic systems, all these systems follow energy principles. So now what you see here is you see different types of elements. You can have mechanical elements, you can have electrical elements, you can have fluid elements, and you can have thermal elements. So here you would see in the mechanical elements, you can have force, you can have velocity. In the electrical elements, you can have capacitor, you can have inductor, you can have resistor. So this is the inertia element. This is the damping element. This is the resisting element, or this is the resisting. And then basically you can have capacitor, you can have inductor, you can have resistor. In the fluid elements, you can have reservoir, you can have an accumulator, you can have a boundary transfer. In the thermal element, you can have the heat transfer across the slab or the pipe. So in the mechanical elements, typically the mass elements are considered as A-type or inertia elements, and constitutive equation for the mass type elements are given by Newton's second law, and then power equation is given as force multiplied by velocity. Then if you go to spring element, this is transmission type of element wherein it actually flows. Constitutive relationship is the Hooke's law, which is force is equal to stiffness multiplied by deflection, or rate of change of force is equal to stiffness multiplied by velocity. If you go to the dissipative type of element or the damping type of element, which is force is equal to damping coefficient multiplied by velocity. So again, you can have the electrical equivalent elements. So you have capacitor element, which is an equivalent element of inertia. You have inductor element, which is transmission type element, and then you have resistor element, which is the dissipating type element. And you understand from these that the constitutive relationships or energy relationships are similar. Same thing happens with the fluid elements. So you have fluid capacitor, then you have fluid transmitter, and you have fluid resistor. And then finally you see similar elements in thermal, but there is no thermal inductor type of element. Otherwise you have these two thermal types of elements. So this is the summary. These are the different analogies and constitutive relations. Now again, what is the advantage of this? Now advantage of this constitutive relationship or equivalent table is this. If I give you an electrical system and say you are a mechanical engineer, to analyze that electrical system, you can convert that electrical system into a mechanical system, write the equations, and your answers are going to be the same. In other words, sometimes what happens is, if you have a thermal system, I don't know how many of you have studied thermodynamics, but in thermodynamics, you have law of conduction, and there is a concept which is called as thermal resistivity or thermal conductivity. So you can actually represent that thermal element as an electrical circuit or a thermal circuit and use that to analyze that thermal system. So you can actually mix and match different systems together to come up with a system representation that is uniform across different fields. So imagine that you have a mechanical system interacting with electrical system. So what you could do is you can have a representation, you can represent both of these into some equivalent representation, and their relationship will be much clearer if you were to look at the two different systems from the same lens. Then that gives you more understanding, that gives you more mathematical tools and better grasp of the situation. So these are the different elements. Mechanical elements are comparable to electrical elements, comparable to thermal elements, they are comparable to flow elements. These are the through and across variables. So through variables means the variables that are related with the flow, and across variables are the variables that cause the flow. So for example, in electrical system, you have voltage, which is the across, and current that is going through. In mechanical, you have the force, which is through, and the velocity, which is across. Now, mechanical and electrical systems, they go hand in hand, which is the essence of mechatronic systems. So in mechanical systems, you have force. In electrical systems, you have current. In mechanical systems, you have velocity. In electrical systems, you have voltage. And these are the different system parameters that are used to indicate those. Now, the next part which I want to talk about is the concept of natural oscillations. Now, these oscillations are observed in mechanical systems, electrical systems, thermal systems, and even environmental systems or the weather systems. These oscillations, they are because of the energy interactions taking place inside that system. And what we'll do is, after we come back, I will give you an example of the natural oscillation. Then we will talk about from the energy concept why these oscillations occur, and then we will try to derive the differential equation of motion or mathematical model purely based on the energy concept. And the reason I want to talk about energy concept is once you master the energy based formulation, whether it's a mechanical system, electrical system, even quantum mechanical system or weather system, you can use the same approach. It would be a uniform way to model and represent these different types of physical systems. I'm going to stop here for 15 minutes. And then once we come back, I'll continue the discussion. So I would like to briefly talk about this concept of natural oscillations. Now, these natural oscillations are like oscillatory behavior that is observed in many different systems, like mechanical systems, electrical systems, thermal systems, weather systems. And the reason for this type of oscillation is you have exchange of energy. And this energy exchange is an important property because, as you know, the conservation of energy states that energy can neither be created nor be destroyed, it can only change form. And we can use this precise statement, this precise law to derive the constitutive relationship or the dynamical models for different systems. So let me take a simple example. Let's consider that I have this spring and I have this mass. I have this spring and I have this mass. Initially, this spring and mass is in at equilibrium, which means this is the position. This is in equilibrium. Now, what I'm going to do is I'm going to pull this mass down. I'm going to pull this mass down, which means that would stretch the spring. So that would stretch the spring. I pull this mass down and let it go. What will happen because of that is this mass is going to oscillate up and down. So this mass would oscillate up and down. So, and it would exhibit motion something like this. This motion is called simple harmonic motion. And this is actually a natural oscillation because once I initially add a disturbance, remove that disturbance, this mass is going to oscillate up and down, up and down, up and down. So let's understand what is causing this oscillation. There are three locations. This is location A, this is location B, and this is location C. So when mass is at location B, initially the spring was neither stretched nor compressed. What I did, I pulled this mass down, I stretched the spring and let it go. So this mass started oscillating between C and A. So mass is going down At point C, the strain energy or the spring is completely stretched. So the potential energy of the spring is maximum. And the mass is reversing, it's going down, and at point C it reverses, which means the velocity is zero. So what happens is the potential energy is maximum. Since velocity is zero, kinetic energy is zero. When it goes all the way in the top, the spring is completely compressed, so potential energy is maximum. Kinetic energy is zero. At center, the potential energy is zero, but kinetic energy is maximum. So what is happening? There is continuous transfer of energy from potential energy to kinetic energy and kinetic energy to potential energy. That is causing this system to oscillate back and forth or up and down. So if I want to use this concept, this energy relationship, I can say something like this. The potential energy of the spring is 1/2 kx square. Because if you think about the spring, if x is the displacement of the spring, F is the force of the spring, the area under this curve, which is 1/2 F times x, and F is force, which is stiffness multiplied by x. So this gives me 1/2 kx square, and then I have kinetic energy, which is 1/2 mass times x dot square, if m is the mass. So the total energy is equal to potential energy plus kinetic energy, which is 1/2 kx square plus 1/2 mx dot square. And since the energy can neither be created nor be destroyed, so I can take the derivative of this total energy, d by dt of total energy, and I equate it to 0. So this becomes 0 is equal to 1/2 2 kx x dot plus 1/2 m 2 x dot x double dot. And please understand, x dot gets cancelled, 2 gets cancelled, 1/2 gets cancelled, and what do I get? I get mx double dot plus kx is equal to 0. Are you with me so far? So this is the exact same equation that we derived earlier, wherein we had mass, we had spring, which is k, and then what we did is we used the Newton's law to derive this expression, but the same expression can be derived using energy principles. Total energy is equal to 0. I mean, total energy is constant. So rate of change, if you take the derivative of total energy, that is equal to 0, and mx double dot plus kx is equal to 0. The next part is how do we express these expressions into state space. Now please understand, remember this, if you have a second order differential equation, you get two first order differential equations. If you have a third order differential equation, you get three first order differential equations. if you have a fourth order differential equation, so second order means you have x double dot. If third order means you have x triple dot. So what happens is state space representation is converting a higher order differential equation into the first order differential equation. Now, typically, the state space representation is given by something like this. X dot is equal to AX plus BU. Now, what I want to do is, I just want to take the same example. Say you have a spring mass, and on this spring mass, we have an external force U of T. This is K, this is M. So let's take this exercise and try to convert this into a state space form. So this equation becomes mx double dot plus kx is equal to U of T. Now here, I'm going to assume x and x dot as state variables. So I have the relationship something like d by dt. State variables go here, x dot. State variables go here, x dot. And then this forcing comes over here. So U of T 0, 1. So you have 0, 1. Then you are going to have minus K by M 0. So this equation becomes x dot is equal to, I change the sequence. This will be something like 0, 1 U of T bx, sorry, ax plus bu. So this is A, and this guy is B. Now what is Cx plus du? So imagine what you have is, you have maybe a Doppler radar or a speed gun. And what this speed gun can do is just like the speed gun that is used by cops. It can only give you the value of the velocity. So what this means is y is the output. So what is the output? Output is x dot. And this x dot is nothing but x dot 0, 1. And D is the control input. So basically this would be 0, 0 of T. So this is the state space representation of the spring mass system. Everyone understood this? So if you have a mechanical system, if you have a differential equation, once you know what is the input, what is the output. So in this particular case, the output is x dot and input is u. So you can derive or you can write down a relationship between the input and the output, and you can come up with the state space representation. So here are some examples that are talking about the state space representation. Again, state space is non-unique, so you can definitely use different types of elements. You can use the combination, and you can come up with a different representation of the state space. What are the properties of the state space? State space is the minimum set of variables that describe the system. And then what you have is, you have the causality property, which talks about the future state is dependent on the input and the current states. And then what you have is you have the n dimension state space that actually encompasses all the possible trajectories that that particular system can take, all the combination of state space. Then state space has this transformation that does not have memory. So which means it only depends upon the previous state. It doesn't depend upon states two states before or three states before. So basically, those are the properties of the state space. And many a times you can have a linear state space system, which is shown over here. So for example, all these systems which are shown over here, they are linear state space systems. And you can also have a nonlinear state space system. You can have a nonlinear, non-autonomous state space system, which means time t is explicitly present in the state space formulation. The other important properties of the linear state space is you have something called as the principle of superposition, which means you can actually indicate an additive property. You can add multiple responses together to find out the overall response. And for linear systems, that is absolutely required. The system is linear if and only if the principle of superposition is maintained. Now, there are concepts which are called as the input and output model. So what you do is input-output models are basically the mathematical relationships between the input and the output. State space is one of the input-output model, but there might be some different formulations. They can give you a different input-output model that may not be in the state space. So state space is one possible representation of input-output model. You can have linear input-output model. You can have non-linear input-output model. And basically, so for an example, this is the same example that we talked about, wherein what you have is the spring constant is 0. So what you have is, so in our equation, we looked at mx double dot plus kx is equal to u of t. In this, k is equal to 0, which is mx double dot is equal to u of t. So in this particular case, you can treat them as two types of output models. So in first case, you consider position as your output. In the second case, you consider velocity as your output, and then you would get these output models. So depending upon what you are interested in studying, whether you want to just consider position as an output, or if you want to consider the velocity as an output, you can have two different representations. Now, how do we develop the models? And then clearly what we do is we understand the purpose, look at the variables, come up with approximations, draw free body diagrams, use energy relationships, look at the continuity relationship, look at the compatibility, and then eliminate the auxiliary variables, the variables that are floating around that we don't need, and express the mathematical relation in the most compact form. So these are the ways we can actually construct a state space model. And this example I just showed you, we constructed a state space model for the spring mass system, and we followed this technique, these steps, all the way from 1 to 5. Now, here is one simple example. Now, I just want to take this example is because this is a practical system. And clearly, this practical system is actually a complex distributed parameter model. So what you have is, we have this pump, and this pump is driven by a diesel engine, and there is this flexible shaft that is attached to the diesel engine and the pump. And what we want to do is, we want to come up with an expression that provides us the relationship between the input and the output. So first and foremost, what we need to do is we need to perform some simplification. So we need to perform simplification. So what we are going to do is we are going to assume that this model is a simple a linear model. So this has the damping, this B, it has the stiffness, it has the inertia. Then what I'm going to do is I'm going to draw the free body diagrams of this two separate parts. So I'm going to separate out these two parts. This is one part and this is the other part. So what I'm going to do is I'm going to write down, I'm going to show the free body diagram of the shaft, which is flexible, and I'm going to show the free body diagram of this inertia. The one thing to note is this impeller is having some fluid friction, fluid resistance. So this fluid resistance is indicated as B times omega. And then the next step, what I'm going to do is I'm going to write down the differential equation for this guy. I'm going to write down the differential equation for this guy, and then I'm going to combine these two differential equations. So in the first part, if you look at the motion of the shaft, the derivative of torque, d torque by dt is equal to the torsional stiffness and the change in the speed, omega 1 minus omega. If you look at the inertia properties here, the constitutive relationship that we have is we have B1, which is the damping, capital omega minus omega 1 is equal to torque. Now what I do is I can combine these two equations together, and that gives me this one relationship. So what I did, I eliminated the auxiliary variables and finally got only one equation out of these two relationships. Now next thing is I want to look at this for the shaft. Now next thing is I have to look at the rotor. So I have J omega is equal to T minus T2, and the torque which is dissipated is damping B2 times omega. So I can combine these two relationships and I can get this relationship. So I have one equation for the shaft, one equation for the rotor. I use these two equations and represent them in a state space. And again, I am not focusing on the physical derivation of this equation, but I want you to understand, and we will solve quite a few problems. I'm planning on solving 3 to 4 problems in next class, where we will actually come up with these expressions. But here, what I want you to understand is I want you to understand the process. What is the process? In the process, we have this physical system. This physical system is a complicated system. It has pump, it has shaft, it has coupling, it has inertia, it has impeller, it has fluid resistance. This is actually a distributed parameter system. To come up with a mathematical model, what I need to do is I need to come up with a simplified system, a simple system. The simple system is represented on the right hand side. That is, I'm going to assume the system is linear. Then what I do is I actually separate out the shaft and the rotor from each other. Then I use Newton's laws and write down the free body diagram and come up with the forces, in this particular case, torques on each of these elements. So if I look at the constitutive relationship for the shaft, I have the change in the torque, rate of change of torque is equal to K, which is the torsional stiffness multiplied by change in the angular velocity. And then I have the energy, or the energy that is dissipated, B times multiplied by omega, which is the damping factor multiplied by change in the angular velocity, is the torque that is dissipated. And then I substitute that relationship for torque into the first relationship, and then I got one expression for the shaft. I do the exact same thing for the second, that I have the rotor, then I have the inertia properties of the rotor. So the first equation is j omega dot is equal to T minus T2. Then T2 is equal to B2 times omega. I combine these two equations and I get one equation for rotor. So now I have one equation for shaft, I have one equation for rotor. I combine these two and I got this state space model for this combined system. This is a linear system. I can simulate this, I can analyze this, I can use some type of a numerical software simulation and actually come up with the behavior of the system. Now, please try to understand this system that we showed over here. This is sort of a rotary system. We have the shaft that rotates, we have the inertia or the rotor that rotates, but I can represent this system as an equivalent system which comprises of two masses. As you can see, there is one mass on the top, one mass at the bottom, springs. That spring indicates the shaft stiffness, and the damping, which are the dampers which are shown over here. So what it means is, if I write the differential equation for this system, you will exactly get the differential equation that we derived earlier, but this is the representation where I'm assuming the translational motion, not the rotary motion. So what it means is you can use a different type of representation, but still you would be able to come up with the same mathematical behavior. Now, imagine if you have a vehicle, so, and you have a suspension. So, and what I want to do is, I want to come up with a mathematical model of this suspension. So you have spring, you have damper, and then what you have is, here you have cab, and then here again you have dampers and other stuff. So you have tire, you have this wheel and axle, you have the suspension system, and you have the mass of the body. 1/4 because there are 4 wheels. So if you have this car, then you can separate out the individual components and represent them as spring, mass, damper system to come up with the mathematical model for the system. And again, I'm going to work out a few problems in next class, wherein I would actually start with a simple system, and then what we will do is we'll go through the iterations and we will work out, we'll derive the motion. Then what we will do is we will use that and then find out the response of the system and so on. So I would take these examples in next class, but what I want to do is I want to take this opportunity to discuss something related to MATLAB. Now, very quickly, let's look at what we have so far. So what I want to do is, I want to say that we looked at the first order system, we looked at the second order system. Now the question is, how do we solve this system? So let me take a side note here. insert this slide. So we talked about this system. So this is K, this is B, this is M. Differential equation of motion is mx double dot plus cx dot plus kx, and what I'm going to assume is there is some external force f of t. And say f of t is equal to sine t. So this equation is mx double dot plus cx dot plus kx is equal to sine t. How do I solve this differential equation? I'm going to explain solution of this differential equation using maybe 2 or 3 techniques. So please bear with me. First and foremost, I'm going to use this expression as is, program this in MATLAB, and try to solve this differential equation. I will take this system as is, I will program this in MATLAB and try to solve the system. In the second case, I would use Laplace transform and try to solve this. So what happens in Laplace transform? In Laplace transform, the independent variable t gets converted to independent variable s. X dot gets converted to s times x. X double dot gets converted to s square x. X of t gets converted to x of s. So when I make all these substitution, this expression gets converted to m s square x of s plus c s x of s plus k x of s is equal to, I'm going to call this capital U of s. So U of t, U of s. And then what I do is I try to solve this equation in Laplace domain. Third thing I can do is I can create a transfer function. Transfer function is nothing but Laplace transform of output divided by Laplace transform of input. My output is x of s. My input is u of s. So this is going to become 1 divided by m s square plus cs plus k. So now what I'm going to do is I'm going to use MATLAB to basically solve this system of equation. But MATLAB would need some values. So I'm going to assume for the demonstration m is equal to 1, then c is equal to 1, and k is equal to 2. So these are the values that I'm going to use. So I'm going to use MATLAB, and then I'm going to program, and I would strongly recommend that if you have MATLAB, please open MATLAB with me and then program and follow my lead, and we can do the programming. So now I'm going to shift my screen and I'm going to start MATLAB. So share screen, MATLAB, share. So let me home. So then what I need to do is I need to go editor, home, preferences, increase the font. So what I'm going to do is y is equal to dsolve d2y plus 2 times y 2 times dy plus 1 times dy 2 times y is equal to sine of t. Then I need to supply the initial conditions y of 0. I'm going to say y of 0 is equal to 10. Then dy of 0 is equal to 1. So this equation, so dsolve since these are the initial conditions, they need to be like this. And then what I'm going to do is, so this equation is basically going to solve the differential equation in the closed form. So how do we solve this in Laplace transform? SYMS. I'm going to create S, T, and Y, capital Y. So these are the symbolic variables. F is equal to sine of T. F is equal to Laplace. F comma T comma S, which is going to take T comma S, which is, oh, not sine. No sine. Then dy is equal to S times capital Y minus the initial condition on the velocity, initial condition on the displacement, d2y is equal to S multiplied by dy minus 1, which is the initial condition on velocity, and the solution is equal to solve d2y plus dy plus 2y minus f comma y. And so this is the Laplace, and then I need to take the inverse Laplace, I Laplace solution s comma t, and then I would do plots, figure 1, easy plot, y comma 0 comma 3, figure 2, easy plot, solution 0 comma 3. So this is the solution of the equation. So bear with me. First line, please understand this is the differential equation. Mx double dot plus Cx dot plus Kx is equal to sine t. I'm supplying initial conditions, the initial displacement at time t is equal to 0 is 10. Initial velocity at time t is equal to 0 is 1. So this is how the MATLAB would solve differential equation in the closed form. Next part is I am defining the symbolic variables to solve in Laplace transform. Then I'm describing the function f is equal to sine of t. I'm expressing capital F is Laplace of small f t comma s, dy, d2y. Look at the solution, figure 1, figure 2. And then what I'm going to do is I'm going to highlight this and evaluate selection. So now what I want you to do is I want you to look at the solution from the first solution and the second solution, and please observe that these solutions are identical. Probably my online students can't see these solutions, so let me change the screen. Okay, online students, can you see the solution? And I will show you the code. So that way you will have both of these for comparison. So what you have is on the right hand side, you have the code, and on the left hand side, you have the solution. The first solution, what you see on the top, is the differential equation directly integrated, and the bottom part is the differential equation that is solved using the Laplace transform. Have you understood this? Any question? Everyone got the same results? Good results? No? Yes? Online students, did you get the same results? Yes, no? Any questions, concerns? Everyone got it? No? Yes? Got it? Let's see. Symbolic math. Okay. Yeah. You will need symbolic math. Now the next part is I want to do the same thing with transfer function. So go to Simulink. Blank model. Go to library browser. And in library browser, you can see commonly used blocks. In the continuous. Here you can see transfer function. Let me see state space transfer function. Go to transfer function. Denominator coefficients. This is the coefficient of m. Next is the coefficient of b. Next is coefficient of k. So as you can see that you got the same transfer function that I showed on the whiteboard. Only difference is I substituted m is equal to 1, c is equal to 1, and k is equal to 2. So this is the transfer function. Now what I'm going to do is I'm going to go to the transfer function and then I'm select the input, the sources, and I'm going to say it's a sine wave, and I'm going to attach sine wave. Sine wave amplitude is 1, frequency is 1, no phase shift, sample time 0, click OK. Go to library browser, commonly used blocks, go to scope, grab this scope over here. So, and what you do is, so what was the stop time earlier? Let me see real quick. 3 seconds. So I'm gonna say stop time is 3 seconds. And then model settings, properties. Run. And here you see the exact same curve. The only difference is I didn't supply the initial condition. So what you can do is you can change the initial conditions and then the response of the system would match with the response of the system. So model properties, all that info. So this is how you can simulate the system using Laplace transform, system using the direct approach. And so just to show you, I would change this to 0. I would change this to 0. Palette selection. Yeah, this needs to be taken out. This needs to be taken out. So now observe that all these three results are identical. The first result is from the direct integration of the differential equation. Second result is from the Laplace transform approach. And third result is from the transfer function. I'm going to wait here for a minute so that everyone understands. The first result that you see in figure 1 is like I gave that differential equation and used MATLAB DSolve to find the solution. Then what I did, instead of directly solving the differential equation, I used the Laplace transform technique, but I did not use the tables. I used the built-in MATLAB function, Laplace and iLaplace, to find out the Laplace transform solution. And the last part, what I did, I found out the transfer function. What is the transfer function? Transfer function is the Laplace transform of output divided by the Laplace transform of input. I substituted that transfer function in the Simulink file, and then I gave that an input, and I got the output. Everyone understood this? It's super important. The last part which I want to talk about is what happens. There is one more. Is library browser, and then what I do is continuous. I take this state space, put it over here, and in the state space block I have 0, 1, then I have -1, -2, B is 0, 1, C, D is 0. Can specify the initial conditions. So this is the same equation. The only thing is now it is written in the state space form. Click OK. Of rows in B. So B, yeah, B comma. Number of rows in number of columns. Number of columns in B. Parameter C. Oh, yeah, C. C is going, since we are plotting the displacement, this will be 1, 0. See, a number of rows in the A matrix. Okay. This has 2 rows. This has, okay, this wants like this. Okay. All right. Let me see. 0, 1. Let me make sure that my B should error. Okay, correct. I'm going to feed the same thing. And I'm going to use scope. Then run. So you have this. we have this. I think I made a mistake in one of these blocks. Let me see real quick. So 0, 1, -1, -2, 0, 1. Yeah, so parameter runtime A, auto and Simulink. Oh yeah. So just this is how you can enter the state space form A, B, C, and D, and then you will be able to get the solution from the transfer function or from the state space. So there are different ways of solving the system, and I would strongly encourage you to take a look at different ways of solving the system. And when I actually work out the physical problems, we would spend some more time on how to program those inside MATLAB and get the solutions. So now in the last part of today's lesson, what I'm going to do is we are going to focus on doing some hands-on experiments with TCLab. But before we move on to TCLab, I want to ask if there are any questions. So if there are no questions, what I want you to do is I want you to open and connect TCLab. And so let me show you what we are going to do. So this is the TCLab. Just connect this TCLab. And my hope is that everyone completed this setup and troubleshooting. Did everyone do setup and troubleshooting? Except you, right? Okay, Simulink kept on crashing. Okay. Your Python is not working? Okay, what about MATLAB? MATLAB working, Python working, Simulink crashing? Okay, let's take a look at it. How about others? Okay, so here is what I did. So let me share. So first and foremost, MATLAB. If you go to MATLAB, you should have all these files in the same folder. So MATLAB, there is TCLab, LED, TCLab test heaters, test LEDs, and so on. So just making sure that run this and make sure that this is running. So once you run this code, What you should do is you should be able to see something like this. Did you get this? Now what this is there are two heaters. Those heaters are heated and there are thermistors, and the thermistors are measuring the temperature from those heaters. So you can see that the heater, we are supplying a step input going from 0 to 100, but because of the thermal inertia, the thermistors are not responding very quickly. So the response is gradual. That's what you should be seeing from the very first lab. So let me get you I have a spare. Let me get you a spare. The second part is you can observe that gradually this kind of settles down, and then you would observe that heater shuts down, and then the whole thing you will see it cools off. So you should be able to see that the system is behaving. But please understand what this tells me is even though I have a step input, the system response is gradual. You see that? Even though I have a step input, the system response is gradual. So now my question to you is, what type of system is this? I'll be right back. Once I come back, tell me what would be the best way to describe the system. And possible answers are zeroth order system, first order system, second order system. So look at what we talked about and then tell me what you think would be the best way to represent this system. I'll be right back. Okay, did everyone get the same response? So now tell me, is it the first order system, second order system, or zero order system? Second, first order system. It's not exactly a first order system, because what I want you to observe is very important. And my online students, please observe this. even though the system response is gradually going up, the output starts responding after some time. Have you noticed that initially this period is like output is sleeping, nothing is going on. And what is the reason for that? Because the thermistor is a thermal paste that is attached to the thermistor and the heater. So there is actual time delay between the response of the system and the input, which means observe. To turn it on, but the output does not start at time t is equal to 0. It starts slowly. So basically, this is something called as the dead time. Dead time means the system is not responding. System takes some time to respond and then it is sluggish. So if we want to approximate this system, the best way to approximate this system is the first order system with a dead time. Okay, first order system with a dead time. So what we are going to do is we are going to look at, okay, online students, any questions? So it is first order because please observe that there is this trend. It's not instantaneous. There is no oscillation. Now I can answer your question in two ways, but okay. First and foremost, let's go back to Simulink. Let's go to Simulink. Create model. And what I'm going to do is browse library, go to continuous transfer function. How would the first order system look? The first order system would look something like this. And what I'm going to do is I'm going to add a step input. Let's see if there is any step input here. Sources. Step. And then I'm going to add scope. Online students, can you see what I'm doing? So to answer Devesh's question, what I did, I quickly created a Simulink block. And this is the first order system. Here, why is the first order system? First order system is y dot is equal to tau y. So basically, this system is the first order system. Y dot plus tau y. This system is S y of S. So this is like U of T plus tau y of S. This is U of S. So I would take y of S outside. So this will become tau S plus 1 y of S is U of S. The transfer function. This is my output, y of S. This is my input, U of S. 1 tau s plus 1. And I'm assuming tau, which is the time constant, as 98. Are you with me so far? This is the first order system representation. And now, my online students may not be able to see this, so I'm just going to show them using the Zoom. Let me see if I can show you. Online students, can you see the work on the board? Okay, yeah, I need to flip this. So this is, let's see, yeah. Can you see the math on the board? Yeah, so this is okay. All right. So now what I'm doing is go to MATLAB, and what I've done right here is this is the simulation. Run this, and now look at the scope, and you can see you have the step input, and then what you have is, so the step input got attenuated. So this is like the system is behaving. I want you to look at this. Do you agree with me that the behavior that I showed you here, it's similar to this observation here? So I want you to track the red line. Can you see that this red line is something similar to this? The only difference is here the system doesn't respond immediately. There is dead time. So what you want to do is you want to add a dead time here. So basically that is called as the transport delay. And this transport delay, it's common. Why is this transport delay? Because this is very important. I want you to observe the heater and the thermistor. I don't know, have you noticed it changed color? Initially it was purple, now it is black, because it is a thermal epoxy. So what that tells you is that epoxy is hot. Don't touch it. That's why the red LED light is on. Okay, that it's hot. So that's why the epoxy changed color. So please notice that that thermistor is not at the exact same location as the heater. There is a physical space in between these two. That's why this delay is coming in the picture. So now what I do is I actually change this time delay to 10, step response 0, final one I'll say 100, and now run, and what happened? So basically so now observe this response and this response is similar. Now some of you may say, oh, it doesn't look very similar. So to make sure that it's similar, let's go to TCLab. And what you can do is actually if I is equal to 1005 and then run. Now you will notice observe. Again, this is not like something special. What we have to do is we have to get the data from the system and then perform the experiment, and then we find out the right function for this particular system. And you would observe you have to wait till 1000 all the way. So you will observe that the trend will be something similar. Okay, any questions from my online students? Okay, so yeah, okay, so what I'm going to do is I'm going to stop this, Control C, and I want to give you assignment for today, and please try to do this assignment in class. If not, you can continue doing this at home. So the assignment for today is I want you to go to TCLab website, and then I want you to go to one heater and then read through this lab. And then you can do this TCLab file for single heater. Then this actually shows you something called as first order model with dead time, FOP dt. This is the first order model or first order polynomial with dead time, and then it's exactly same thing as what I have done in today's class. So please watch this video, download this file, download Simulink file, run this, and then by next Tuesday, write a short report, no more than 2 pages, a short report on this assignment, and I will show you what you will do. So you will go to TCLab CISO. You will do test models, and then basically you will run this as a live script. And once you start running this as a live script, you will observe that it will perform the experiments in real time. Actually, it will get the data and it will generate the plots. So I'll just wait for a minute. Done. So check this out in the live script. You would see that it will automatically generate the first order model, and then it will actually create the first order model with dead time. And then I want you to read through the theory on how to do this lab of the first order model with dead time and complete a short report of 2 pages. And it will be due next Tuesday. So upload that onto Canvas. And how to do this lab is very simple lab. It should not take you more than 15 minutes to complete this lab. You can do it with just one way. I prefer to do it with MATLAB, but if somebody wants to do it with Simulink or Python, that's totally fine. So once again, let me repeat. I want you to go to this model one heater. So this model is just the basic modeling. So I want you to go one heater, read through this lab. And then there is this single heater model code that I want you to read and then perform this lab. And there is a companion video that you can watch, and then actually you should be able to get the data. So please try to understand what is first order differential equation with dead time. Click here. This actually tells you how to do the first order model with the dead time. Are you with me so far? I will repeat. Step 1, go to this lab, Arduino dynamic temperature modeling. Watch this video. Download this MATLAB file. Run this. It's a live script. It will generate the data for you automatically. But then what I want you to do is read first order plus dead time this and create a mathematical simple model. It's very simple, should not take you more than 15 minutes. And it actually just write a 2-page, you can actually type a 2-page report on this assignment. Everyone understood this? You are welcome to finish this lab in class. If you have any questions, I would be happy to help. So I would strongly recommend that you do this lab in class. but if you don't want to do it in class, you are welcome to, yeah, you can do it differential equation in Python. As a matter of fact, if you go back here, there is Python code for differential equation in Python. So this is Gecko Python source code. This will do differential equation in Python. So first order plus dead time. Please try to understand this is a very simple mathematical model for first order plus dead time. Here we have to find out two parameters. One is the time constant. Second one is the gain of the system, and third one is the delay. So what I want you to do is I want you to read through this lab, watch through this video how the first order plus dead time is calculated. Here this is the video, and then repeat this lab on the TCLab setup. So online students, have you understood this? Okay, you cannot get the page right now. Okay, what I'm going to do is I'm going to put this page in the chat window. The hyperlink in the chat window. Online students, are you on the same page? Did you get the same page? Okay. Now please do this lab. It's better if you do it in next 25 minutes because I would be here to help you. And this lab should not take you more than 15 minutes to complete. Download these files, TCLab files for single heater, and quickly watch this video. This is for 5-minute video. And then look at this video, which is FP OPT. Copy. So this will actually show you how to do this lab. Okay, so I'm gonna add this note here. So project 2. Complete. Heater 1 lab. So complete Heater 1 lab. For some reason Zoom is slow. I need to stop my video. Okay, so yeah, complete Heater 1 lab. Perform first order plus dead time modeling on Heater 1, right? Or type 2-page report, 2-page individual report, and upload in Canvas. And this report will be due by 12th, due 7, 12, 22, 11, 59 for Tuesday. And the links are already uploaded in the, you should be able to see the links. Okay, any questions here? But you have to perform what is the first order plus dead time, find out the point. And probably you may have. Okay, what I want you to do is run the given script first. Everyone found the script? So, the live script. Run that script. The script I just ran. Yeah. Okay. Let me, probably I was not very clear, but what I want you to do is I want you to run this live script. So test models.m, MATLAB CISO. Did everyone get this? Where would you get this? You will get this over here. This download MATLAB TCLab scripts. 4 files. All of four of those. You will need all 4 of those. So download TCLab files from here. Now I need to share the screen. So go here, download TCLab files for single heater. It will download 4 files. Open these 4 files in desktop. Out of those 4 files, look at test models, test_models.m. And please run this file, test underscore models dot m. Are you able to run the live script? Online students, are you able to run the live script test underscore models dot m? Excellent. And what it should do is it should run interactively. It should run the first order model. It should get some type of data from the first order. Now you will notice if you go down, everyone with me so far? So if you read through this code, it's actually running this automatically. But what I want you to do is I want you to click here. Watch this video. And from this video, find out the process gain, the time constant, and the dead time or the time delay, which is theta p. So once you run this first order plus dead time model, the experiment, the data that you get here will allow you to find out that model. In the lab you right? If you have any questions, I would be happy to answer any questions you have. You understood this? Please try. If you get stuck, I would help you. And I'm going to stop here today. Online students, any questions? Have fun doing the lab. And the lab, if you have any questions, if you are not able to get the results, I would be happy to help you out again on Tuesday. But please play with it. And then you will see that how the system is behaving. So if you look at here, that you have the temperature that is actually measured, then you have this energy balance equation, and then you have this first order model with dead time that's kind of tracking the system. So just take a look at the code. So it's a very straightforward MATLAB code. Yeah. Yeah, you can do the first assignment and upload it. That's fine. Yeah, actually, yeah, I gave the rubric also what needs to be done. Uploaded the video. It's in the video. Yeah. Okay, I'm gonna stop here, and I will see you all on Tuesday.